Good day, everyone. My name is Chris Marine, and I'm the Chief Operating Officer at McObject. Thank you for joining us for our webinar, Internet of Things, Implications on Database Management. We have a very interesting session for you today. For IoT applications to perform as optimally as possible, the developer needs to pay special attention to how the data is managed in the application. Of course, most engineers appreciate that, but making the best choice for the type of DBMS to use can be very challenging due to the many choices, architectural differences, and unique requirements of your application. Our session today is designed to help you identify and educate yourself about the approaches that should be considered based on the type of data you're working with. First, McObject CEO Steve Graves will take you through our main presentation, which examines the considerations for choosing the most appropriate database management system for your IoT project. After that, we'll have time for questions based on the presentation and about database technology generally. You'll be able to submit your questions using the Q&A window at the bottom of the screen. So to get the show rolling, let me take a moment to tell you a little bit about who we are. McObject was founded nearly 20 years ago with the unique goal of bringing to the market a highly optimized DBMS for embedded applications, thus eliminating the need for homegrown data management tools. Since our inception, our high-performance products, ExtremeDB and Perst, have been used in applications including networking, consumer electronics, medical, military, and aeronautics, embedded controllers, and many other vertical solutions. This success has fueled our growth with staff and customers in locations throughout the world and millions of applications which have been shipped using our technology. I'd like to introduce you to Steve Graves, our co-founder and CEO, who will be covering our topic today, IoT Implications on Database Management. Steve has been involved in embedded database architecture and engineering for over 30 years and brings a wealth of experience in solving real-world problems in the arena. Steve?
Okay, thanks, Chris. There's three broad topics that we'll cover in today's presentation. First, I'm going to give a high-level overview of embedded systems versus the IoT Edge. Next, there'll be a brief discussion about exactly where the edge is, because there's conflicting marketing messages from players in IoT that have created some confusion in that regard. But we'll spend most of the time delving into what is different between embedded systems before the IoT and IoT Edge devices. So with that, let's dig in. When talking about their solutions for edge computing, some database vendors would have you believe that gateways are the edge of the IoT world. That's simply because they don't have a solution that can run on the true edge. The old saying, if the only tool you have is a hammer, everything looks like a nail, comes to mind. For example, Microsoft talks about deploying a SQL Server database to an IoT Edge device. They're talking about a Linux device, one that's hefty enough to support SQL Server and that runs on AMD 64 or ARM32 or ARM64. So forget about MIPS, PowerPC, Coldfire, and other embedded processors that we often see on the IoT Edge. That quote comes from the URL that's shown on the slide. Don't worry about trying to write that down real fast. Chris is going to put it into the chat window so you can copy and paste it from there. Our view is that the edge is the intelligent connected devices, not gateways. IoT devices could be smart thermostats, set-top boxes, routers, industrial controllers, wearable tech, and so on. The possible examples are almost limitless. The common attribute is that they connect to gateways. So gateways are not the edge. And as I said, unfortunately, this has led to confusing messaging from database system vendors. I want to emphasize that by and large, gateways are not the edge of the IoT. The edge is the systems or devices that are directly connected to the data generation, whether that is, for example, an industrial sensor or an automobile's camera, the LiDAR or radar. So, what's different between embedded systems and IoT Edge devices? Just as a quick aside, the term Internet of Things, or IoT, was first used in 1999 by a gentleman named Kevin Ashton who had started the RFID Research Consortium when he was at MIT. But the term IoT, or Internet of Things, didn't really enter the popular lexicon until 2008 or 2009. Okay, back on the topic. If embedded systems and IoT edge devices are devices with relatively slower CPUs, less memory, and less storage than desktop PCs, workstations, and servers, then how are embedded systems and IoT edge systems different? When we came out with the first database system created explicitly for embedded systems in 2001, we were mostly dealing with data silos, meaning that the data was captured on the device and never left the device. For example, portable media players need a database system to manage tracks by artist, album, genre, maintain playlists, and so on. The data movement was one way. Once you downloaded the music to your device and the database was built from the MP3 metadata, that was it. The owner had everything they needed to search and play music. Likewise, a television set-top box needed a database to store the channel and program information coming from the satellite transponder or the cable head end, but the data movement was one way. Today's set-top boxes are a little bit more sophisticated, but kind of irrelevant to my point. You can still find examples of embedded systems as silos, but for the Internet of Things, the story is completely different. The purpose of the Internet of Things is to collect data and make it useful in some way. And part of the reason for the explosion of the Internet of Things is the wonderfully diverse ways that data can be made useful. Making data useful means that it must be collected, aggregated, shared, and analyzed for some purpose. So enter the modern IoT database system. Whereas embedded systems databases largely only had to deal with managing data on the device, an IoT Edge database system has that and additional challenges to solve. Another evolution in embedded systems to IoT Edge systems is the prevalence of multi-core processors. As you know, taking advantage of multiple processing cores doesn't magically happen. It takes effort to write your code to be multi-core aware and not inadvertently cause blocking and serialization of execution. It requires even more effort to retrofit a large body of code like a database management system that was written before multi-core processors became prevalent. For context, Intel released the Core 2 Duo in 2006. So when you're researching your choices for a database management system for your edge device, look into its ability to leverage a multi-core architecture, or at least not hinder your ability to leverage a multi-core architecture. To put a finer point on it, some implementations of the C runtime library for embedded systems toolchains are still rather rudimentary, and a database management system's reliance on the C runtime library can defeat concurrency in a multi-threaded application. For example, relying on malloc and free to manage heap memory. Worse yet, the database system itself can hinder the ability to leverage multiple cores. For example, very popular embedded database SQLite uses pessimistic concurrency control, for which the lock granularity is the entire database. So a task that's writing to the database blocks every other task that wants to read or write to the database. In this case, a concurrent task that otherwise would be able to execute in parallel on another core is going to be put into a waiting queue. Embedded systems were largely homogeneous, meaning that developers only had to worry about a single target hardware platform. For example, the Apple iPod used an ARM7, end of story. Database management systems for embedded systems always had to deal with the ability to support different target platforms, or what we call platform independence, which is unlike desktop and server systems that are predominantly x86 based. Embedded systems could use ARM, MIPS, PowerPC, ColdFire, Easy80, Tile64, and more. But the data itself didn't need to move between systems. So being able to build with different tool chains for different target platforms and different operating systems was enough. In other words, the database system code needed to be portable, but the data didn't need to be portable. In contrast, an Internet of Things system is often heterogeneous. In other words, many different hardware platforms. For example, there might be a Raspberry Pi wearable device, which is an ARM32 architecture, that connects to a gateway running x86, which in turn connects to cloud servers that might be running Power 9 Linux systems. Now, a database system implementer has a new wrinkle with respect to platform independence, in that we have to be able to move data between architectures with different endianness, different alignment requirements, different word sizes, and so on. So make sure the database system on your short list have got this covered. One of our customers makes lighting systems for large events like concerts. Unfortunately, their business has been hit really hard by the pandemic because, there's no big events going on right now. But their use case is emblematic of this heterogeneity that I'm talking about. Engineers will generally use a PC to develop a lighting program, which is then distributed to various other devices that could include smartphones, tablets, and lighting consoles. The program can be updated in real time on any one of these devices, and that change has to be immediately reflected in every other device. Generally, in their system, there are 20 or so such systems that the database must be distributed to, which in turn is controlling thousands of lighting fixtures. That distributed database example is actually a good segue into the next topic, which is connectivity. As I mentioned at the outset, in embedded systems, if there was a need to move data around, it was, for example, for high availability, which also implies that the data was moving between like systems. In other words, the systems were homogeneous. So replicating from one ARM to another ARM, or one MIPS processor to another MIPS processor. And in addition, we could assume a reliable and a high-speed network between the master database and the replica database. We can't make either assumption with the Internet of Things. An IoT system might have battery-powered devices or devices in remote locations and or mobile devices. And that has a couple of implications for database systems. For example, will a database system support Bluetooth Low Energy, Zigbee, and or LoRaWAN to replicate data from the edge to gateways? The next implication is that the systems that are battery powered or mobile could have intermittent connections, almost certainly the case for battery powered systems. Database systems can't assume an always on connection, and will need to have the ability to know what data has been replicated and what data is waiting to be replicated, and a policy for how to manage the circumstance when more data accumulates than the device can hold during a prolonged period of being disconnected. Our solution to this problem is called the Active Replication Fabric. And again, Chris is going to copy these URLs to the chat window for you. The first link is to a web page that describes the Active Replication Fabric. The second link is to a page that describes a demonstration program that we created to showcase the Active Replication Fabric, which you can download and run on your own. Or you can just watch Chris give a demo of it at the third URL there for YouTube. A few words about security. The database on a set-top box or a portable media player or an industrial environmental chamber didn't really need to be secured. But the database underlying a messaging application on your smartphone or a video surveillance system or any number of medical systems certainly do need to be protected. A database system for the Internet of Things should be able to protect the data stored on a device and ensure the security of the data while it's in transit from edge to gateway, between gateways, and ultimately to the cloud. That should be another checkbox on your list. The embedded systems examples I've used previously in this discussion had data architectures that fit nicely into a more or less relational database design. For example, the portable music player has artist, album, and track entities where there are one-to-many relationships between artist and album and between album and track. So a conventional row-oriented database system implementation worked really well. In the IoT world, however, we're often managing so-called time series data, which is a sequence of data points usually paired with a timestamp that represents the changes of a thing over time. The most common example in the Internet of Things is sensor data. For example, a remote weather station can gather temperature, atmospheric pressure, and wind speed measurements. A smart energy meter can gather kilowatt hours of electricity used at points in time. Time series data is most efficiently stored in a columnar fashion, not a row-oriented fashion. Recognize that most database systems store data organized much like a spreadsheet. There are database pages that hold rows, and each row consists of some number of columns. So a weather station's data might be organized like this. With this organization, if a client program wants to calculate the average temperature at a weather station for a range of time, the database system must read entire pages of station IDs, timestamps, temperature, pressure, wind, and wind direction, when all the program is really interested in is the first three attributes. In other words, the station ID, the timestamp, and the temperature. The I/O processing for the latter three attributes is just wasted I/O. For this use case, a better way to organize the data is for a database page to contain only the values of a single column, so no I/O is wasted. In other words, a page would consist of only values of the temperature field, because that's what we want to do the calculation on. So in this case, we still have a row for station ID and its attributes, station latitude and longitude, and then we have vertical storage for the time series data. Note that the time series data tends to be highly repetitive, and so it lends itself to a highly efficient compression algorithm known as run length encoding. Simply, if the value 45 reoccurs 197 times, it's only going to be stored one time with a counter to indicate the number of occurrences. We might need only 8 bytes of storage to represent this versus 197 times 4, or 788 bytes if we didn't use run length encoding. In our experience, run length encoding typically yields about 90% compression, and that's going to pay dividends in storage space, I/O, computation, and replication. That superior organization of data has resulted in time series database systems increasing popularity, dwarfing all other database system models in the last 2 years, as you can see on the slide here. IoT devices have the potential to generate a tremendous amount of highly granular data. Consider a sensor that samples data at 1,000 hertz. That's going to be 86,400,000 data elements per day. A device with 10 sensors, each producing a double precision floating point number, would generate nearly 7 gigabytes of data every 24 hours. It's entirely likely that for local processing, that level of granularity is required. For example, in an industrial control system, a controller may need to be able to react instantly to measurement changes. But farther up in the IoT ecosystem, it's unlikely that that fine-grained data is useful. Ideally, an IoT Edge database system will have the ability to aggregate data and replicate only the aggregated data to the gateways and the servers, especially when the Edge device has low bandwidth and/or intermittent connectivity. While standard SQL aggregate functions can do the basics, like sum, min, max, average, etc., more advanced capabilities like window aggregates, grid aggregates, standard deviation require more advanced analytics. To put a finer point on it, rolling those 1,000 hertz samples up to a grid average of 1 second reduces the data transport and upstream storage requirements by 99%. Most, if not all, large database vendors have recognized the need or the customer demand for in-database machine learning and addressed it in some way. Just go search for SQL Server machine learning or Oracle machine learning, and you'll see what I mean. Examples of machine learning and artificial intelligence are pretty easy to find in big data. For example, credit scoring agencies can combine information regarding an individual's current debt load and payment history with other data regarding shopping trends and other behaviors to draw correlations between those behaviors and past credit performance to predict future performance. IoT Edge database systems that facilitate machine learning are somewhat more of an emerging technology. Virtually every embedded database vendor that offers an SQL API offers the usual SQL aggregates, again, min, max, average, sum, etc. But you have to search a bit harder to find embedded database systems that support more complex analytical functions that are essential to machine learning, such as correlation, covariance, deviation, and others. Examples of machine learning at the IoT Edge are harder to find, but consider an adaptive transmission as one example. An adaptive transmission is one that learns your driving patterns and modifies the transmission's performance accordingly. In other words, the adaptive transmission might delay shifting if it senses high lateral acceleration, or provide snappy shifting for an aggressive driver, or softer shifting for a more laid-back driver. The arguments for in-database machine learning at the edge are largely the same as for machine learning in the enterprise. It's a simpler architecture versus knitting together disparate technologies. This could be particularly important in resource-constrained IoT Edge or embedded systems, which simply might not have the resources to host a complex tool like Kafka and everything that it entails, or that might simply not be available on a given architecture. Also, it avoids having to move a lot of data between systems, even if those systems are running on the same target system. As I mentioned previously, edge systems can generate a lot of highly granular data, and it's usually not desirable to replicate such granular data. So the data ends up being downsampled or aggregated or somehow summarized, but that would compromise the quality of machine learning. So machine learning at the edge can be very useful. So analytics should scale. Here's what I mean. We're going to use one of our customers, Schneider Electric, as an example. They make a smart building system to retrofit older buildings that were built in the pre-IoT era. Now, my discussion here may not be an entirely accurate reflection of what their system actually does, so much as an exploration of what it could do. If I'm a building manager, I'm interested in how my building is performing, where I could be monitoring the HVAC, the security cameras, water, door locks, or access control system, electricity, and more. I'd want to be notified if, for example, security camera is offline, or that water consumption is unusually high, which might indicate a burst pipe somewhere. Incidentally, this picture you might recognize being the Microsoft campus in Redmond. On the other hand, if I oversee an entire campus of buildings, then the analytics that I have access to should change accordingly. And again, someone at corporate would want to have a whole view of the system. For each of these scales, the building, the campus, and HQ, ExtremeDB's ability to store and analyze time series data, downsample it if necessary, and utilize the active replication fabric to transfer the data upstream is invaluable. So that concludes my presentation for today. We have plenty of time for questions and answers, so I'm going to turn it back over to Chris to moderate the questions and answers.
Very good. Thank you, Steve. So as Steve indicated, I'd like to take questions from the audience now. You can type and send questions from the Q&A box on the bottom of the screen. And let's see, I see we already have one. The question comes from Chris. He asked, does ExtremeDB support blockchain-based security features?
So the short answer is no. ExtremeDB, so the security features that ExtremeDB supports are either built-in AES-64 encryption for data at rest, or you can plug in your own encryption module. And then we rely on TLS or SSL to secure the data in flight.
Okay, thank you, Steve. Let's see, we've got another one here. This question comes from Roy. If columnar databases are better, why didn't you just go with a columnar database instead of this kind of hybrid that you seem to have?
Yeah, good question. So simply put, the conventional row-based databases handle conventional data better. Columnar databases have, pure columnar databases, that is, have a reputation for performing poorly when you're doing a join. So we want to have the best of both worlds in ExtremeDB. We wanted to be able to perform joins and do normal OLTP type processing exceptionally well. But we also wanted to be able to support the time series data exceptionally well. So having this hybrid approach meant that we don't have any of the disadvantages of a pure columnar database, and we retain the advantages of a conventional row-oriented OLTP type database.
Thanks, Steve. We got another question that's coming here from Shiva Kumar. The question is, what is the memory footprint of ExtremeDB?
So the minimum footprint for ExtremeDB core is between 100 and 150K, depending on the tool chain and the target architecture. If you throw everything in, so that would be the core plus the SQL API plus high availability and application replication framework, et cetera, then you could be looking at a code size that's 400 to 500K, but still pretty modest.
Great, thanks, Steve. AJ asks, does ExtremeDB support continuous queries? For example, a machine learning feature creation such as multiple window aggregates, such 30, 60, 100-day totals, average spend, etc. Or is it better to do this in real time for multiple 50+ features required for machine learning algorithm?
So we don't directly support continuous queries, or active queries as they're sometimes called. What we do offer is a couple of features, one called data relay and another called persistent queue of events. The latter is probably more applicable to this use case, where ExtremeDB instantiates a pipe, and we're pushing event data into one end of the pipe, and your application is reading that event data off the other end of the pipe. And using that, you can exploit that scheme to simulate or emulate continuous queries.
Okay, very good. We got another question about machine learning. It says requires raw data. How does ExtremeDB handle the transport issues for intermittent connection scenarios and the sheer volume of data?
Okay, so that's part of the active replication fabric. So I'd encourage you to go either watch the YouTube video where Chris is demonstrating the application, and he's going to demonstrate exactly that capability within the active replication fabric. But briefly, the active replication fabric is aware of whether there's a connection to the upstream device, whether that's a gateway or a server. And if there is no connection, it'll simply queue the data on the device. If it's an in-memory database, then of course an in-memory database is finite in size. So it's got the ability to tell you how much space you have left, and then translate into how long that device can remain offline before it's going to start losing data.
All right, thanks, Steve. And on a related question, Roberto asked, is Active Replication Fabric a separate product?
No, it's built into ExtremeDB.
Okay, great. Mike asked, thin/heavy seems to come to mind when I see your architecture. It seems ExtremeDB seems to promote the idea of that doing more on the edge is a better way. I realize you promote that a small memory footprint, but won't doing more on the edge use more CPU? What is your argument to that?
Give me 1 second here. I'm reading the question here. Okay, so yes, doing more on the edge implies that you're going to be using more edge processing power. I would say that the processing power on the edge, when you aggregate the processing power of many, many, many edge devices, probably exceeds the processing power at the gateway, or potentially even at the server. So I don't know that that's a bad thing. And I think that's a large reason that edge computing has become such a large trend.
Okay, good, Steve. And I see we got another one here from Andrea. Can Active Replication Fabric replicate from ExtremeDB to another database?
No. Active Replication Fabric is an ExtremeDB product, if you will. So it replicates between two ExtremeDB devices. Answering a previous question, I mentioned Data Relay. Data Relay was built for just that, to be able to replicate from ExtremeDB to any other system that's not ExtremeDB. That could be a protocol stack if you needed to update some quality of service parameters, or it could be another an enterprise database like a SQL Server or an Oracle, and many of our customers do that, moving data back and forth between ExtremeDB for real-time stuff and enterprise databases for whatever they do up there. So Data Relay, much like the persistent queue of events, is going to instantiate a pipe, and it's going to be shoving transaction data into our end of the pipe, and you're going to be pulling that transaction data off the other end of the pipe and doing whatever it is that you need to do with it, you know, an insert into a SQL Server or an Oracle or an upsert or whatever it might be.
Okay, great, Steve. Let me remind everybody, if you have any other questions, please type it under the Q&A section at the bottom here. Let me also point out that we will be recording this session, or actually are recording this session, and we will have a link available here fairly soon that we will communicate to everybody who is in the webinar, so you can review it on your own and watch it again. So at this point, I guess, Steve, I don't see any other questions. Thank you for attending our webinar. It's our hope you gained a good understanding of how important choosing the right database management solution can be for a successful IoT project and implementation. Thank you today, and have a good day.